All right, let's dive into AI video generation today and the Step-Video-T2V model. And this thing, it can generate high-quality videos. You give it text prompts, and it'll spit out videos. And we're talking up to 204 frames, which is really impressive, blows most other models out of the water.
Yeah, I mean, this is a game changer for those of us in AI research and ML engineering for sure.
Absolutely. And so we're going to break down their technical report today, go into architecture breakdowns, training strategies, comparisons to other models. So we'll talk about Hunyuan Video and Runway Gen 3.
Yeah, and we want to respect everyone's time. So for the first minute, we're going to do like just the highlights, a little summary, but definitely stick around for the full deep dive. This paper gets into some really interesting challenges and future directions for the field.
Yeah, so real quick, just a high level, the Step-Video-T2V model, it's state-of-the-art. It's got 30 billion parameters, generates those 204 frames that I mentioned. And what's really cool is that it can handle both English and Chinese prompts.
And they do that with some pretty impressive bilingual text encoders they've built.
Yeah, and we'll talk about that a little more. But also we've got to talk about the efficiency, right? I mean, video data is massive. So they're using a special Video-VAE that compresses video data 16 times spatially and 8 times temporally. And that's really key for making training on a massive scale even possible.
Yeah, that was really cool. That was one of the things that jumped out at me too. But yeah, you think about it, right? If you didn't have that compression, how are you going to be training these models? It would just take forever.
Right. And what's even crazier is that even with all that compression, the quality is still top-notch. And they're even beating out some commercial engines in areas like high motion dynamics, which is really wild.
Yeah, I was looking at some of the comparisons. Really impressive stuff.
Absolutely. And then the cherry on top, it's open source. They're making both the model and their evaluation benchmark public, which is huge for research in this area.
Oh yeah, this is going to be a massive boost for the whole field. Everyone's going to be jumping on this.
Okay, so let's get into the paper now. One of the things that I thought was really interesting was this idea of video foundation models. And they talk about like two levels, right? You've got the translational and then you've got the predictive.
Yeah, that was a really interesting distinction. The translational one, that's basically what we're seeing now. Like you take text, convert it into video, but that predictive level, that's where things get really wild.
Yeah, imagine AI that can like forecast events in a video based on what's already happened. Almost like how LLMs predict the next word in a sentence, right?
It's mind-blowing to think about.
Mind-blowing. And so the Step-Video-T2V model, it's still at that level 1, that translational level, but even so, it's pushing the boundaries in terms of what's possible. And they're dealing with some serious computational challenges. And this Video-VAE that we talked about, that's like key for handling just the sheer size of video data.
Yeah, it's like they figured out how to shrink those massive video files down to something manageable, but without losing the quality. That's the key.
It's incredible.
And they get really into the nitty-gritty of the system optimization. They're talking about parallelism strategies, specialized kernels, load balancing across GPUs, all that stuff. It's like a masterclass in large-scale training efficiency.
So, okay, let's talk about the training strategy because this is also super interesting. They actually start with text-to-image pre-training, which I thought was kind of counterintuitive. I would have thought you would just go straight to video. But they actually found that going straight to video slowed down the learning process.
Yeah, that's interesting. So it seems like giving the model that foundation in image generation first helps set it up for better performance when it comes to video. Like it's learning to crawl before it can walk or something.
That's a good analogy. Yeah, like they need to understand images first before they can really grasp the complexities of video. And then they transition to low-resolution video training, right? Before bumping it up to higher resolution. So the idea is to get the model focusing on those motion dynamics early on.
Yeah, they're like, okay, let's get the movement down before we worry about making it pretty, basically.
Right, and then, okay, this is where it gets really cool. So they use human feedback, specifically direct preference optimization, or DPO, to fine-tune the model.
Yeah, that's pretty slick. It's like having an art director for your AI. They're basically refining the output to align with human aesthetics and preferences.
Absolutely. And I mean, the team is also very upfront about the limitations of the model. They acknowledge that generating complex actions, like a gymnast doing a routine or something, that's still really challenging, even for a 30 billion parameter model.
Yeah, and accurately simulating physics in a video, like a ball bouncing, realistically, that's also something that still needs work. They're very honest about that.
Right, and it's important to be upfront about those limitations because we don't want to overhype things. But the fact that they're even getting close to that level of realism is pretty amazing.
It is.
And then, one point they emphasize, which I think is super important, is that even with all this advanced tech, the quality and diversity of the training data, that's paramount. That's like the foundation of everything.
It all comes back to the data. If you don't have good data, you're not going to get good results. Garbage in, garbage out.
Exactly. Okay, let's shift gears a little bit and talk about some of the future directions they outlined in the paper because they have some really interesting ideas.
Oh, yeah, they do. One of the things they're looking at is combining autoregressive and diffusion models. They think this could be a way to generate more natural and fluid motion in the videos.
Right, because right now, most models generate each frame kind of independently, so you don't always get that smooth flow of movement that you see in real life. This could be a way to address that.
And another interesting idea is exploring RL-based optimization. Reinforcement learning has been super successful in other areas of AI, like game playing and robotics, but applying it to video generation, that's still pretty new.
That is really intriguing, especially when you think about training AI to accomplish specific goals within a video, like almost teaching it to solve problems visually, which is a wild concept.
It is, and then there's this idea of creating a giant video knowledge base with structured labels and everything to fuel even more sophisticated models in the future, like building a library of visual understanding for AI.
Okay, so we've covered a ton of ground here in just the first few minutes, so let's take a quick pause and then we'll come back and really get into the nitty-gritty of how this model works.
Sounds good. I'm ready to dive deeper. So we got to talk about this Video-VAE. This is the heart of how they're dealing with these massive video files.
Yeah, video files are huge. It's a big problem, right, for training these models and even just for using them.
Exactly. Imagine training a model on, hours of raw footage. It would take forever. So that's where this Video-VAE comes in. It's like a super efficient compression algorithm, but designed specifically for video generation.
Okay, so they're basically shrinking those files down while losing the important information, right?
Exactly. It's like they're creating a blueprint of the video, all the essence, but none of that bulky data. And they've designed the new architecture. It uses 3D convolutions and this thing called pixel unshuffling.
Pixel unshuffling? What is that? Sounds like something out of a video game.
Okay, so imagine you have a messy room, right? Furniture everywhere. Pixel unshuffling is kind of like rearranging the furniture in a really clever way to optimize the space. So in this case, they're rearranging the pixels, and it allows the model to capture both the fine details and the overall structure of the video.
That's cool. So it's about preserving the important information while still getting that crazy compression.
Exactly. And the result is this Video-VAE that can handle all the complexities of video data, but in a really efficient way, which is, super important when you're dealing with these huge models.
Now, I know they didn't just stop at designing this Video-VAE, right? They also had to come up with a training process for it.
Yeah, they have this multi-stage training process. They start with a smaller compression goal, less ambitious, and then they gradually increase the complexity step by step.
Got it. So they're not just throwing everything at the model all at once.
Right. It's like building a strong foundation before you start adding the complex stuff on top.
That makes sense. Okay, so we've got this powerful Video-VAE handling the compression side of things. What about the text encoder? This is what allows the model to actually understand those text prompts, right?
Yeah, this is where the model takes human language and turns it into something it can work with. And this is where it gets interesting because Step-Video-T2V actually uses 2 different bilingual text encoders.
Wait, 2? Why 2?
Well, think of it like each encoder has its strengths, right? So you've got Hunwan Clip. This one's really good at generating text representations that are aligned with the visual world, but it can't handle really long or complex prompts.
Okay, so it's like a sprinter. Good for short bursts, but not for marathons.
Exactly, and that's where Step-LLM comes in. This one is designed for those longer, more nuanced prompts. It can handle those complexities.
So by combining those two, they've got a system that can understand a wide range of prompts. Short, long, simple, complex. It's pretty clever.
It is. Now let's talk about the core of the model, the DAT with 3D full attention.
This is where the magic happens. This is where the text prompts actually get turned into moving images.
Exactly. DIT stands for Diffusion Transformer. And so instead of using a typical spatial temporal attention mechanism, they went with 3D full attention. This allows the model to consider both the spatial and temporal information all at once.
So it's not just looking at individual frames, it's understanding how those frames relate to each other over time.
Right. It's like seeing the whole picture, not just the individual pieces. And they made some cool tweaks too. They've got cross attention, which allows the model to pay attention to the text prompt as it's processing the visual features.
So it's like the model is constantly checking back with the instructions, making sure it's on track and creating a video that actually matches the prompt.
And they added things like adaptive layer normalization and rope 3D, all these optimizations to make the model more efficient and powerful.
Okay, so they've got this powerful DIT with 3D full attention. They've got all these optimizations. Now they need to train this thing. How do they do that?
So they use this technique called flow matching, which is kind of different from the more typical DDPMs, denoising, diffusion, probabilistic models. Essentially, flow matching, it trains the model to predict the direction and magnitude of change, like from an initial noisy input to that final clear video frame.
Got it. So it's not just removing noise, it's learning how to create the video, how one frame flows into the next.
Exactly. And then during inference, they use this clever ODE-based method to gradually refine the noise step by step until they get that crisp, high-quality video.
Now, we talked about this earlier. Their use of human feedback with DPO, that seems like a really important part of their process.
It is. It's all about aligning the model's output with what humans actually like. They show human annotators pairs of videos generated from the same prompt, and they just ask, which one do you prefer?
A blind taste test, I like it.
Exactly, but they found that sometimes the improvements from DPO would plateau, like the model would hit a wall.
Oh, interesting. So even with the human feedback, it wouldn't necessarily keep getting better.
Yeah, so they came up with this solution. They trained a separate reward model.
Okay, a reward model. What does that do?
It's basically like an AI film critic. It's trained to evaluate the quality of newly generated videos during training. And the key is that this reward model is periodically fine-tuned with new human feedback.
So it's like they've created this feedback loop, right? Where both the main model and this reward model are learning and improving together.
Exactly. It's a pretty elegant solution. But they didn't stop there. They also tackled the issue of inference speed. Diffusion models can be really computationally expensive.
Right. Nobody wants to wait hours for a video to generate.
Right. So they developed this technique called self-distillation, which basically creates a smaller, faster version of the model without sacrificing too much quality.
So it's like a streamlined version ready for prime time. Okay, let's talk about data. I mean, they obviously needed a ton of data to train this thing. Where did they get it all?
They built this huge data pipeline to process raw videos and extract the good stuff. Billions of video text and image text pairs.
Billions. And I'm guessing they didn't just grab any random videos off the internet?
No, they had this whole multi-stage filtering process to make sure they were working with high-quality data.
Like a team of video editors curating each clip.
Yeah, pretty much. They used scene detection algorithms to split the videos into clips. Then they evaluated those clips for things like aesthetic quality, watermarks, subtitles, any kind of, weird stuff that might mess up the training.
So they're really trying to make sure the data is clean and high quality.
And they also use this technique called concept balancing to make sure that the data set wasn't dominated by any one category. Like, they wanted to represent a wide range of concepts and scenes.
Makes sense. You don't want the model to be biased toward one particular type of video.
And then, this massive data set that was for the initial pre-training phase, for fine-tuning, they curated a smaller, higher quality data set, focusing on videos with good motion, realism, aesthetics, and of course, accurate captions.
So for fine-tuning, they really wanted the best of the best.
Exactly. They even had human annotators review and refine the captions to make sure they were super accurate and detailed. It all goes back to that garbage in, garbage out.
Okay, so they've got the data, they've got the model architecture, they've got the training process down. How did they actually train this thing? What was the strategy?
So, multi-stage approach, right? Pretty common for these complex models. They started with text-to-image pre-training, which might seem weird, but they found that training the model on images first actually helped it learn faster when they moved on to video.
So it's like they're giving the model a basic understanding of visual concepts before they jump into the complexity of video.
Exactly, like learning your ABCs before you start writing novels.
I like that analogy. And then, okay, so they move on to text-to-video training. But they didn't just jump straight to high-resolution videos, right?
Right. They started with lower-resolution videos first, let the model focus on the motion dynamics, get that down, before worrying about the finer details.
Okay, so kind of a gradual ramp-up in complexity. Makes sense.
And once they had a pre-trained model, then they moved on to fine-tuning. This is where they really hone in on specific tasks, like generating high-quality videos from text prompts.
And that's where they use that smaller, curated data set we talked about, right?
Exactly. They actually experimented with different fine-tuning techniques and found that averaging the weights of multiple models, each fine-tuned on a slightly different data set, that actually worked best.
Huh, interesting. So it's like combining the expertise of multiple specialists.
And of course, they all incorporated that DPO stage, using human feedback to really refine the model and make those generated videos even better.
So to summarize, they've got this multi-stage approach. Pre-training on images, then low-resolution video, then high-resolution video, and finally fine-tuning with human feedback. And they did all of this on a massive scale, with thousands of GPUs.
Yeah, it was a huge undertaking for sure, but the results are really impressive.
So how do they know how well this model actually performs? How do they measure that?
Well, they didn't just rely on standard metrics. They actually built their own benchmark called Step-Video-T2V evil. specifically designed to test these text-to-video generation models.
Okay, so what makes this benchmark special? What kind of challenges did they throw at it?
Well, it's got 128 Chinese prompts collected from real users covering a bunch of different topics and styles. They wanted to make sure the model could handle the kind of stuff people would actually use it for.
So it's like a real-world test, not just some theoretical benchmark.
Right, and they used 2 human evaluation metrics because, video quality, that's subjective, so it makes sense to get feedback from actual humans.
Yeah, absolutely. Numbers can only tell you so much. At the end of the day, it's about how people perceive the video. So how did they actually get the human feedback?
For the first metric, they showed annotators pairs of videos, one generated by Step-Video-T2V, one by a different model. But the annotators didn't know which was which. They just had to say which one they preferred or if they thought they were equal.
It's like a blind taste test for AI-generated videos.
Exactly, and this gives you a good idea of how Step-Video-T2V stacks up against other models.
Okay, that's cool. And then the second metric, you said they went a bit deeper, right?
Yeah, so instead of just asking for a preference, they had the annotators rate the videos on 4 different dimensions: instruction following, motion smoothness, physical plausibility, and aesthetic appeal.
So they're really breaking it down, trying to understand the strengths and weaknesses in more detail.
Exactly, and the results were really good. Step-Video-T2V performed well across all 4 dimensions, especially motion smoothness and physical plausibility. Which makes sense because they really focused on those things during training.
Right, it seems like their efforts paid off. Now, I thought it was really cool that they were so open about the challenges they faced in developing this model. It's not often you see that level of transparency in research papers.
Yeah, I agree. It's super helpful for the whole research community, sharing those lessons learned so others can avoid making the same mistakes.
Absolutely. So what were some of the biggest challenges they ran into?
Well, we talked about the computational resources needed to train a model this big, right? 30 billion parameters, weeks of training time, thousands of GPUs. It's a massive undertaking.
Definitely not something you can do on your laptop. It really shows how much investment is needed to push the boundaries of AI research.
Yeah, for sure. And they also talk about the limitations of current video captioning models, which can be a problem because the model relies on those captions to understand what's happening in the video.
Right, if the captions are bad, the model's going to learn the wrong things. It's like trying to learn a language from a textbook full of errors.
And then there's the whole challenge of incorporating human feedback effectively. We talked about DPO, but it's not perfect. Human feedback can be subjective, it can be sparse, it's hard to scale.
Yeah, there are definitely some limitations there. Okay, so big picture, what are the key takeaways from this deep dive into Step-Video-T2V?
I think it's a major step forward for AI video generation. This model is really pushing the boundaries, showing what's possible. It's beating some of the commercial models out there, and it's open source so everyone can benefit from it.
It's amazing to see how far this field has come, and it makes you wonder, what's next? What's going to be possible in 5 years and 10 years?
I don't know, but I'm excited to find out. It feels like we're just scratching the surface of what AI can do with video.
I agree. This is a field that's moving so fast, it's hard to keep up. But that's what makes it so exciting, right? Well, I think we've covered just about everything. Thanks for joining me on this deep dive. It's been a blast.
It's been fun. Always great to chat about this stuff.
And thanks to everyone listening. We'll see you next time for another deep dive into the world of AI.